Let's do the 1993 mechanics free response problem number 2. And I really like this problem because it really shows you how to use exponential functions. Remember, you use exponential functions a lot with RC and RL circuits in E&M, but here's an example of how we use exponential functions in a mechanics problem. So, let's do it. Here's a little car. It has a mass of m, initially at rest at t equals 0, is driven to the right as shown above along a straight horizontal road with the engine causing a constant force F naught to be applied. While moving, the car encounters a resistance force equal to negative kV, where v is the velocity of the car and k is a positive constant. Now the dot below represents the center mass of the car. On this figure, draw and label vectors to represent all the forces acting on the car as it moves with a velocity v to the right. Okay, so let's do that. Well, of course we have this F naught, right? That's actually it's the static friction between the wheels and the road, right? But it's propelling the car to the right. So let's draw that. F naught. And what else is acting on it? Well, we've got this resistance force, and it's going in the that negative just means it's in the negative direction, or it's opposing. Actually, the negative means it opposes the direction of the velocity, and since the car will be moving to the right, this force kV will be to the left, and that's the resistance force. And then, of course, we've got gravity, or the weight of the car, mg, which is the weight, and then we have a normal force that supports the weight, and which is the normal. And of course the weight and the normal force really aren't going to have much to do with this problem. So there you go. Maybe you should label this the resistance force and this the, I don't know, the applied force of the car. But I'm sure that'll get you full credit if you just did that. Now, part B. It says, determine the horizontal acceleration of the car in terms of k, v, f naught, and m. Now, this one's really easy if you've drawn the free body diagram. And I'll just do it on the paper here. It says, determine the horizontal acceleration of the car in terms of all that stuff. Well, looking in the x direction, first of all, the acceleration is going to be in the x direction. I think you can see that. So let's sum the forces in the x direction. That will be equal to ma in the x direction. Now, looking at the forces here, it's F naught minus, this is in the negative x direction, kV is equal to ma. And so now we can just express that acceleration. Solve for the acceleration is equal to F naught minus kV over m. And that's my answer. You see, it's the acceleration in terms of this stuff. We did it. Don't have to go any farther than that. Now, for part C, and this is the most interesting problem, part of the problem, it says derive the equation expressing the velocity of the car as a function of time, t, in terms of k, f naught, and m. Now, this is where it's going to be an exponential function. And let's figure out why. Okay, let's look at this car. Let's just think of it quantitatively. Qualitatively, just conceptually. Look at this car. At t equals 0, there is no velocity. If there's no velocity, then this force right here doesn't exist. So this is supplying all, so we get F naught is our net force. So we have maximum acceleration. But as the car accelerates to the right, the velocity becomes greater and greater, which means that this kV becomes greater and greater. So as time goes by, the net force decreases until eventually we get a zero net force, in which case the car won't accelerate anymore, in which case this kV has reached its maximum. And so I think you can see that the car's velocity is going to start at 0, it's going to accelerate very rapidly, but then as kv becomes greater, it will slow the rate of acceleration until the velocity becomes constant. Okay, now let's actually derive this mathematically. Excuse me. So let's start off with acceleration. Well, what is acceleration? It's dv dt is equal to f naught minus kv over m. Now this is a differential equation. In terms of velocity, you have velocity and you have its first derivative in the same expression. We want to solve this differential equation. Now, when you have a variable and its first derivative in an equation like this, you're going to get an exponential function. That's something to look for. Now, the way you solve a differential equation like this is you separate variables. That is, you put all the v stuff over here and you put all the time stuff over there, which is easy to do. This is dv over f naught minus kv is equal to dt over m. And we've separated the variables. But I want to get velocity by itself, and I also want it to start over here. So I'm going to change a few things here to make this something that we can actually integrate. First, let's get rid of the k in front of the v. And what are we going to do? We're going to multiply both sides of the equation by 1 over k. Now, what does that give me? Well, it gives me dv over f naught over k minus v. Yeah. And then over here, we get dt over m divided by k. Now, I want the v over here. So I'm going to multiply both sides by -1. So this gives me dv over v minus f naught over k equals negative, let's just reciprocate and multiply here. This is k over m times dt. Well, now I'm ready to integrate. I'm going to go from 0 to v, 0 to t, right? Because at time t equals 0, it's starting from rest. And at some arbitrary time t, we're going to call that velocity v. Now, this is dv over v. So that's going to be the natural log of this thing. So this is going to be the natural log of v minus f naught over k, evaluated from 0 to v. And this is going to be negative k over m. Well, you sum all the little dt's, you get t, evaluated from 0 to t. Oh, I'm off screen, sorry. Okay. Well, if I put in v here, and then you put in 0, I'm going to kind of skip through the natural log rules here, but what you end up here with is natural log of v minus f naught over k. That's when you substitute in v. But when you substitute in 0 for v, you get negative f naught over k. And why am I dividing? Because when you subtract with natural logs, you can also take the natural log of the quotient. So review your natural log rules if you don't remember how to go from here to here. And this is going to be negative km over t. What am I going to do now? I'm going to take the natural log. I'm going to raise both sides to the power of e. And I'm going to do it up here. So, well, let me just rewrite it. Let's start over here. So this is the natural log of v minus f naught over k all over negative f naught over k equals e to the k. I'm just rewriting it. Okay, that's what we started with here. Now I'm going to raise both sides as powers of e. That's going to get rid of the natural log. So this gives me v minus f naught over k over negative f naught over k equals negative, oh, I'm sorry, equals e to the negative km over t. We'll talk about the time constant here in a minute, because there is a time constant there, right? So now I'm going to multiply both sides by negative f naught over k. So that gives me v minus f naught over k is equal to negative f naught over k times e to the negative km t. Right? And now I'm just going to add f naught over k to both sides. So v, and this is what I wanted, right? F naught over k minus f naught over k times e to the negative km over t. And now I will factor out the f naught over k times 1 minus e to the negative km t, and that's my answer. That wasn't too bad. Now, and this makes a lot of sense, okay? And as a matter of fact, what you're going to need to do in part D is sketch the velocity. So here's part D. We're going to sketch a graph of the car's velocity as a function of time t, and we're going to label the important values on the vertical axis. Now, here's the cool thing. I'm going to graph this, right? This is the velocity as a function of time, and that's what they're asking me to graph. But you don't even, let's say you get confused in the math. Let's say somehow you got lost in all of this. You can still draw this graph, even if you can't derive the equation for it. If you recognize, hey, exponential function, all right, exponential function. So what do we know about the velocity? Well, at t equals 0, the velocity equals 0. Let's see if that makes sense in terms of the equation. If I plug in 0 for time here, I have e to the 0. Well, what is anything to the 0 power? It's 1. So you have 1 minus 1. That whole thing is 0, so the velocity is 0. Yay. But it told us in the problem and what was given that the car starts from rest. Now, at first, the car is going to accelerate very rapidly, right? Because that negative kV is going to be, that resistance force isn't going to be very strong. But then, as time goes by, that kV becomes greater and greater until the velocity evens out. And so here's what our velocity, our maximum velocity, is going to approach. Now, there's one way to figure out what this maximum velocity is. Let's go back to the acceleration equation. A equals f naught minus kv over m. Well, if you think about this problem, even without doing part C, if you just think about it, okay, once, where is it? Once this force becomes equal to this, the acceleration is going to be 0, and that's when my velocity is at its maximum. So all I have to do is set this equal to 0, and that will be a velocity maximum. So I'm going to multiply both sides by mass and solve for v, and v is going to be equal to f naught over k, right? And now, so I can label this. This is f naught over k, like this. All right. And there, I think you just got all the points. I would have included the time constant in this problem. What is the time constant? Well, look at the time constant here. the time constant is going to be m over k. If I look at this exponential, if I put this in the denominator, that's the time constant, that's tau, right? This little thing right here is tau. So that's m over k. And so m over k would be right here, right? 0.6 something the way up. All right. Now, it says on the axis below, sketch a graph of the car's acceleration as a function of time. Well, if you've got this graph, you can get this graph. And you can label all the important values on the vertical axis. Okay, it just says on the vertical axis. I didn't notice that before. So that means you don't really have to bother with that time constant. But what if you had a problem where it asks you about the time constant? You can figure it out. Now, well, the acceleration starts off at its maximum value, doesn't it? And then the acceleration slowly goes to approaches 0. So it's this exponential function. Now, what is this maximum acceleration? Well, take a look at this equation. It's when the velocity is 0, right? When the velocity is 0, at time t equals 0, the velocity is 0 because it says it starts from rest, and that's just f naught over m. So I think you could see here that if you just understand the motion of the car and recognize it as an exponential function, but even just think about it, I mean, it's got to be an exponential function. It's got to, the velocity is going to increase like this, but increase at a slower and slower and slower and slower rate. And therefore, the acceleration starts at its maximum and approaches 0 with time. These are exponential functions. And you can get part D and E even if you don't get all the math for part C. Now, one final thing. You can construct this equation from this graph. Okay? Now, if you think about it, it's when you have, if you recognize something as being an exponential function, let me zoom out a little bit. If you recognize, oh, this is an exponential function, well, generally what we have here is this kind of an exponential function where you start at 0 or you approach some maximum, or you start at a maximum and approach 0. You've got two choices. You've got 1 minus e to the negative t over tau, okay, times something out here. Now think about this, when t equals 0, this is 1 minus 1. This is the one you use up here. Oh, okay, so I would use this 1 minus e to the negative t over tau. And you say, oh, okay, well, what's my maximum thing? Well, just by looking at the acceleration equation, oh, okay, this is going to be my maximum velocity, which is f naught over k. And that was my answer to part C. And I didn't even do the math for it. Now, I didn't get tau, but we can actually get tau another way, and I'll show you how to do that here in a second. Now, this one, you don't want to use that because you want this to start at its maximum, right? So e to the negative t over tau. Well, when t is equal to 0, this is equal to 1, which is, and then you want that f naught over m. So this is my equation for acceleration as a function of time. Now, I didn't ask you to derive that. I'm just showing you that you could. Now, what about this tau? Well, when I did part C, right, I mean, we did all this, and the tau came out of it. But there is a little trick you can do. You can start from here. I mean, I think you should be, all of you should be able to get part B. Well, what do we know about the units for this little part right here? Here's V. That's my variable that I am trying to address down here. Let's take a look at that. Just in terms of units. Well, we have whatever the units are for, well, what units do we want? We want meters per second squared, right? This has to be meters per second squared. Well, what is velocity? Velocity is meters per second. Well, I need another second squared. So that means if I put this on the bottom, let's just look at that one term. I'm not doing this very well. Let's just look at this one term here. This V over M over K. Now this has got to be meters per second squared. Now from the velocity, you get meters per second, which means M over K has to also be in terms of seconds. And there's your time constant. The time constant always has to be in terms of seconds. And so if you can finesse that, then you can say, oh, okay, well, tau is equal to M over K. And that's true for both of these. So anyway, it's kind of tricky in some ways. I mean, look, part C, you've got to be pretty good at, you have to recognize how to separate variables, how to manipulate it to get to this answer. And that's kind of tough. But I think you can see now that in terms of graphing, drawing the graphs, you don't need all that math. You just need to recognize this is an exponential function, so I'm going to have something starting at 0, going to maximum, starting at maximum, going to 0. Which quantity is doing that based on the problem? And you can get almost everything. And that's what you want to do on the AP test. You want to get as much as you can in as little time as possible. Anyway, that's it. Thank you.